Okay, yeah.
Cool. Okay, which problem should we start first? C? Yeah. So C is the very classic problem. So you have like a bunch of ranges, and you want to know how many points that are covered, how many integral points that are covered by at least one range. So for this specific problem, the constraint is small enough for you to do a brute force. So basically just loop over the range and have a Boolean checking that those points are covered. However, for a more like for problems that have a higher constraint, what you can do is for each range S to T or L to R, you basically think of the problem scanning from left to right. Then actually I should start my camera, I think. There we go. Okay, so for each like imagine you're scanning left to right, and then for each point you want to know how many ranges are covering that point. So essentially for a range from L to R, you can decode it into you can encode it into um, two types of events. At L, you increase the number of ranges covering the point by one, and at R plus one, you decrease the number of ranges covering the point by one. And so you have a bunch of events. You can sort all of these events. You can loop over them, and then you can maintain the number of points covering the point, covering what you're covering the current point that you're standing on. Yes. Okay. So that's free food. The next easiest problem, I believe, is J. J. Okay. So J is basically a reading comprehension. You're given like a really long text that at the end, what you're looking for is this. So you're given a function. You're basically given like the previous hash, and you want to construct the string transaction. Construct transaction and token such that some conditions are valid. In the problem, the valid condition is that the last 7 digits are all 0. The last 7 digits of this function, given these constraints, are all 0. But you can basically transform that like constraint into something like h of previous hash transaction and token equals to previous hash. And basically you want to find a transaction string and a token integer such that this happens. So if you look carefully at this code, at the end we see this: return v times 7 plus token mod 10 to the 9 plus 7. And we see that token doesn't appear anywhere else before. So we know that token only appears in this specific one. So in this specific line, so we can try to use, we can try to say have token here equals to 0, and then it outputs something, maybe something like a h or something like that. Then we will know that as long as we input token, then the output will be h plus token mod 1, 10 to the 9 mod 7. So that means that you can use some basic modular arithmetic to calculate what's the token needed for this expression to be previous hash. And then you can output those two. Transaction can be anything you want. So in my code. Yes.
No, John. I think they don't require the second hash to equal the first
Yes,
hash.
I know that the
Yeah,
second
yeah.
hash doesn't have to be equal to the first hash, but
And yeah, the key is they want the last 7 digit to be 0. So
yes.
yeah.
Um, but the reason the reason I modified it this way because the previous hash has already had the condition correct. So
Right, yeah.
I just yeah, basically I just changed it to my version. But I think there are other ways you can do it.
There's just like a few edge cases, but other than that,
I don't think there's any edge case.
No,
oh
there
yeah,
is
in the
one.
way that you do it, but like,
Oh,
but the way I did it, there's like a small one, but it doesn't really matter. It's pretty easy.
yeah.
No, I guess even in this case, I think there is a edge case. It's just that the test case doesn't. It's difficult to trigger it. So actually, so Patrick told me about it. So basically, they require token to be to 10 to the 9 minus 1. So the token's range is slightly smaller than the 1 10, than the modulus. So therefore, in edge case, it could be that the token you need is too big to satisfy this.
I see.
But yeah, but it just doesn't actually have. Well, I didn't think of it, and the code just passed. But yeah.
Yeah, same.
Oh, I got a wrong answer, and I didn't know why. I wonder if that was it.
That could be it. Yeah.
Yeah. So maybe we should. Yeah. Let's move on to other problems. The next one, I think it is G. Actually, I think G is easier than J actually. So basically you're given like a bunch of
It
queries.
depends on one's prior knowledge. So yeah, if you have the right knowledge, then G is easy. Yeah.
Basically you're given a bunch of queries. Each query you have to output like the number of factors of a number that is not prime. Yeah. So the answer is basically if you're given like U, then the answer is basically the number of divisor of U minus the number of prime factor of U. So you can pre-calculate, you need to pre-calculate all of these two values first. To calculate number of factor of U, you can loop over every factor and then loop over all of its multiples to add into the factor count. And for prime factor, basically it's the same, but you need to check if the current factor is like a prime or not. And that is easily doable with like prime sieve or anything like that.
Yeah.
So I see. So did you actually code it that way? So
the way I coded it is to directly calculate it, but what I did was to basically loop over to count the factor, you need to have some number, and then you count all of the multiples of it. I just need to ensure that this number is not a prime.
Okay, so I guess I'm wondering. So one way to do it is if you know the formula for number of factors based on the prime factorization. So that's one way to do it. But yeah, I guess so. I did it that way. But I guess okay. So you're saying that it's fast enough if you just compute the number of all factors. So what's the complexity for computing number of factors
the complexity is so like if you loop over 1, then you need to loop over all of the multiples of 1. So that's n.
I see.
And then 2, then it's n plus 2, n minus 2. So basically it's n times harmonic number of n, which is about n log n.
Okay, so I see. So basically, this is in a sense you are doing like offline processing first to compute the number of factors for every number. Because if you start from each number and compute it, then this will not be fast enough, right?
Yes.
Okay, so you are for each of
we can look at the code actually.
Okay,
it's quite simple. So PR here is basically check if the number is prime or not. If it's not prime, then if it's prime, it's actually quite unintuitive that this is the opposite. But if it's prime, then we will mark that all of its multiple is not prime. Or else if it's not prime, then we will update that all of its multiples has the answer plus equals 1 because it has a factor of that number.
Huh.
Yeah.
And
So I
this
guess
is
I'm
n log
curious.
n?
Yeah.
Yes, and log n.
So I'm curious. What did others do? Did others do something similar to this? Or did they do prime factorization?
I did prime factorization except with a sieve that reduces, that like points, I guess, to the whatever it's called, like that has its least, like its smallest prime
Small is the
factor
prime factor of the number. So you
or
are
something like that. Yeah.
using sieve to construct that. Yeah, I did. Yeah.
Yeah, I
So
did the
Riley, what did
same.
you do? Riley? Yeah.
I did the same. I did like finding prime factorization with the
I see.
sieve.
I see. Yeah, but I guess that's This cool. Yeah.
Cool. Okay, the next problem, I think it's D. Yeah, it's D. Hoppers. Okay.
Yeah, I think I used this problem in last year's practice or something. I don't.
Did we?
Yeah.
I didn't notice.
I don't really remember.
Did Richard remember this?
No.
Problem? No. Okay.
But
Yeah.
it's not that bad.
Yeah. Yeah.
Oh, it has a few edge cases that is a bit annoying. Also, I did misread the problem, so okay, cool. Let's do some drawing. So in this problem, you're given like an undirected network. Okay, so this undirected network works as follows. Okay, so you start at some node X. Like at each point in time, for each of the node that is marked, you will mark all of the nodes that has distance 2 to that node. Not like least distance of 2, but any node with distance 2. So for example, from this node, you mark this node because it has distance 2 from this, 1, 2. And you mark this node because it has distance 2 from that. Also, then you just continue this process. This node has distance 2 from this node also has distance 2 from this, so this is marked. Okay, so at the end, if you are not, if you haven't cleared the board, then you lose. Like if if subnodes hasn't been marked, then you lose. You want to win this game by basically adding as little edges as possible into this graph. So what you can possibly do is to add this edge. So now you can start from here, and then from this you can mark this, this, and this. And then from this state you can mark this because like this has a distance of 2 from this, and you can also mark this, and now you win the game. So what you want to do is to find the least number of edges, such that if you start from some node, then you can basically infect all of the other nodes. Okay, so a very important thing to know is that you need the graph to be connected first in order to like infect all of the nodes, because if the graph is not connected, then how can you travel to other nodes? So first you need to connect all of the components together using some edges. And now here comes the amazing part. I don't know if it's amazing or not. I can claim that if like a component has an odd cycle, then that component can be infected. Like all of the nodes can be infected. That is because I can start from this cycle, and then I can go around this cycle to cover all of the nodes, basically something like this. From here, goes to here, goes to here, goes to here, and goes to here. And now, because all of the nodes are infected, let's say we have some other node that is connected like this. This node will be infected by the node that is connected to this. And we can repeat that process to like infect every other nodes. And vice versa, if like in we can also show that it's a necessary condition. That is, it is necessary and it's sufficient. Like if it does not have an odd cycle, then we know that it's a bipartite graph. And if it's a bipartite graph, then you can only color like one side of the bipartite graph, and you cannot color the other side. So from here, if you start from here, you can only color these this side. If you start from here, you can only color this side. So what we want to do is to create, if the graph is not, if the graph is bipartite, if we connect it, then we need to add one more edge to make it not bipartite. So does that make sense?
Yeah.
Yep. Okay. Cool. Okay. So the next problem should be, oh, E. I think E is the next problem. Riley, you should do E.
All right. It's geometry time.
Okay.
Wait, why does it say my mic's muted? You can hear me, right?
Yeah, we can hear.
Okay.
Can you share your screen?
Yeah. Oh wait, I didn't want whiteboard. I wanted to share. Okay, that's good.
No.
Okay, so problem E. Quite simple to state. We have a bunch of points, and we want to find the largest area of a triangle containing 3 of those points. That's all it is. We have, and the constraint is 5,000. So, if you want a really large if you want a really large triangle, you can recall that given 3 points, the area of the triangle is given by half the cross product of like 2 of these vectors. So it's 1/2 of the absolute value of u cross v, right? So this immediately would give an n cubed solution, but it doesn't. It's not good enough for us. So now let's think, so to get it down to n squared, let's suppose like we fix a pair of points. Suppose we fix a pair of points, then which one makes the largest triangle? So another way to think of the area of the triangle is base times height divided by 2. So the base is fixed, and then the height is just how far it is in one of these 2 directions, right? So if we fix a segment, we are looking for, we only need to care about these 2 points, the 2 that are furthest in these directions orthogonal to the line segment, right? Okay. Now, let's suppose we have some triangle. I claimed that we can find a better triangle, like we can find an optimal triangle where all 3 points are on the convex hull. So let's see why that's true. Let's suppose that a point, at least one of the points is not on the hull. I'll draw the hull right now. So let's suppose that we can pick this point, which is not on the hull. Then let's say we want to show that we can replace it with a better point. So we can look in this direction and then pick the farthest point in this direction. And because the hull is convex, the farthest point in this direction will be a vertex of the convex hull. So that's the farthest point in the entire convex polygon, which contains all of the points. So we could actually replace this point with one in the hull and make a bigger triangle. And then we could repeat that again. So say this one is not on the whole, then we can replace it with the farthest one in this direction, and so on. So now we know that, so the triangle should have 3 points on the convex hull. So now we can just consider the convex hull of the set of points and ignore everything inside. Okay. So again, we have to bring it down to n squared. So we can't consider every triple of points. But let's suppose like we fix 1 point. Let's call it A. And then we iterate over point B. So point B will like iterate in a cycle. So we'll try this as B, then we'll try this as B, and so on. And then as we scan B around the polygon, we're also going to maintain, let's say this is our current B. We're also going to maintain C, which is the best point to make a triangle with it. So now, let's say we increment B. Then we're also going to increment C as long as it improves the answer. In this case, it doesn't. So now let's see, this one's B. And we want to find the farthest one in this direction. And then we see that moving along this edge improves the area. So we iterate C. And then iterating again would decrease the answer, so we stop. So essentially like we iterate over all A and B, and we're also iterating over C, but as B does 1 pass around the polygon, C also does only 1 pass. So it's like the same idea of 2 pointers. That's a terrible P. So essentially it's like for all A, B and C are the 2 pointers that we iterate over. So for a given, so as B increases, C will only increase because the direction orthogonal to this line segment will only like rotate counterclockwise. So the point that we're looking on for C will only increase. So the complexity is we have n log n for the convex hull, and then we have n squared because we have 1 factor of n to iterate over A, and then the other factor of n is to iterate over both B and C. Any questions?
Cool. Okay, good. Yeah.
All right. Okay, we'll return with this. Okay, so E is the easiest next problem. I think I will talk about B first. I think personally A is easier for me, but B is more standard. Okay, so the problem is something like this. So, how should I? No, not like this. Excuse me. There we go. Okay, so you're given like n junctions with m conveyor belts. So you can think of this as n nodes and m one directed edge on a graph. I think it's directed. Yep, the conveyor belt works in one direction. So there's one directed edge along the graph. And we know there are k producers that are located at the first k junctions. So they're located at the first k nodes. And the producer at junction J will produce at the minute that is modulo equivalent to J, like that is equivalent to J in modulo K. So it will produce like every k minutes that starts from j, basically. And you will want to like have as many machines, as many of these producers functioning as possible, but there's a restriction. You will want like all these producers to travel along the conveyor belts to reach node n. However, the restriction is that at each moment in time, for each conveyor belt, you cannot have more than one product going over it. And at a junction, you can have as many products as you want, but for each conveyor belt, there's a restriction on one product going over it. So, for example, I don't know if this works. What the hell? Okay, cool. Yep. So, for example, let's say this is junction number 1, junction number 2, and this is junction n. So at each the machine at junction number 1 will produce at the minute. Let's say k is equals to 2 first. So these two machines will work. So at the machine at junction number 1 will produce at 1, 3, 5, 7, and at junction number 2 it will produce at 2, 4, 6, 8, and so on. You can see that you cannot actually have these two machines function at the same time, because think about this machine. If it produces at like time moment number 2, then it will travel along, like that product will travel along this junction, and it will reach 1 at minute number 3. So if both two are functioned at the same time, then at minute number 3, junction 1 will have like two products, and those two have to travel to n, which is impossible because there's only one conveyor belt, and those two cannot travel along the conveyor belt at the same time. So you would want to maximize the number of machines, the number of machines that are like active at the same time, such that there's no violation of the restriction. So for this example, it's either letting 1 on or letting 2 on, but not both at the same time. So this problem, you can see very clearly that it has like a cycle. It has a cycle of k. So you can think of this problem as having another state where you can like, for each conveyor belt, it has another state of which time modulo k are we talking about, basically. So you can basically build like a flow where for each conveyor belt at each moment in time, it only has like for each moment in time modulo k, sorry, it only has like one capacity flowing through it. The maximum capacity is 1, and you can also make some edges that goes through like the nodes from the source. So we know that junction I will start producing at minute I. So from the source, you can also have some edges that goes to these nodes I with capacity 1, meaning that we start producing and at the rate of 1 product per minute. And also you would want to have like for n time, for all of these node n time, you will direct it to the sink with capacity of infinity. So you build this flow graph and you basically run flow algorithm to find the maximum flow from the source to the sink.
So you duplicate the edges?
Yes, I duplicate the edges as many times as possible. So for each edge, I duplicated k times.
And the nodes, other than the source and sink, the nodes do not change. It's just
the nodes do change because like because the edge change each
Oh,
edge
I see.
must have a state of time connected to it, then each node also must have a state of
I
time
see.
connected to it.
I see.
Yeah, so I just duplicate all of the nodes k times.
Uh,
Well, that turns out to be passable because flow. Yeah. So yeah, that's this problem.
What flow algorithm did you use?
I used Dynic.
Okay.
So I don't know if other So what's the time limit again? It was 2 seconds. Dynic passed in 0.77. I don't know if
I just used Ford Fulkerson because the total amount of flow is n, is at most k,
I see.
and there's the number of edges is at most kn.
Oh. So yeah, so cubic.
So there was no need to optimize like what flow.
I'm not sure I totally understand, but
okay, sure.
So essentially, yeah, I guess if every node has the time.
So like each node will have like the time state connected to it. This time state is in modulo k because we see that the whole graph is cycling with k. Okay, so for each edge, we want like the edge, this edge and the moment in time. Like we duplicate the edge such that it has also the time state connected to it, and we want like each of these edges to have the capacity 1. It means that only one product can go over it.
okay, and then you just that makes sense then.
Yeah.
I guess you can view these nodes organized as layers, one layer for each time, and then the edge will connect sort of to the next layer.
And then you just try to find the flow to n. Okay.
Yes. Flow
That makes
from
sense.
S to N. Yep. Cool.
It's like I guess this sequence neural network.
Yeah.
So I am actually not sure which problem is the next easiest. I think it is A. However, in my opinion, like A, L, I, which did I solve? K, are actually pretty similar in difficulty.
Just go through any order. Yeah, A is fine, just alphabetical. Well, you want to do K, that's also fine. Yeah.
Oh no, I want to see.
I only looked at A and L. So
yeah, I also.
Okay, let's do L first because A needs a bit of
no, I don't.
A bit of time to talk about actually. So
really?
yeah, I in my opinion it's
okay.
So okay. So in this is problem L. Okay, so problem L, you're given like an array. So this is the array. 1, 3, 2, 4, 1, 5, 2, 4. You want to find like a sequence, a subsequence. It does not have to be consecutive, just a subsequence that is in the form AB. And you want to output like the lexicographically smallest A and B, such that it has this pattern inside this this thing. So in this example, there are actually a lot of, I think there are at least 3 such patterns. One is 1, 2, 1, 2. So 1, 2 is a pair. Another is 2, 4, 2, 4. So 2, 4 is another pair. And the last is 1, 4. You can see why. And you will output 1, 2 because it's the lexicographically smallest. Okay, cool. So I will claim that if there exists like one such pattern, like one such occurrence, one such pattern, then these A's must be like occurrences of the same number, but like consecutive occurrences of that value. And these B's are also the same. There are consecutive occurrences of that value. Okay, so let's think why. So for let's restrict on this let's see how YA works first. So let's say we have this value B here, this value B here. Let's fix these values. And we try to move A forward, and we try to move this A forward, and we try to move this A to the end, towards the end. And as you can see, as long as there's an A before it, then this A can move forward. As long as there's this A after it, then this A can move backwards. So if we finish this process, it means that this like this position does not have any A before it that is to the right of B, and this one does not have any A after it that is to the left of B. So these two must be consecutive. Okay, does that make sense? And for the same reason, we can actually move this B backwards and move this B forward, fixing these A's. And we can also see that these B will have to be like consecutive occurrences of the same value. Okay, so because we know about this, let's construct all of the ranges that are consecutive occurrences. So something like this, something like this. And we have to see that these ranges, like they have to be half overlap, not completely overlapping each other, but not completely separate. Okay, so one natural solution, because we're finding the lexicographically smallest, is to loop over the smallest A possible. And as we loop over the smallest A possible, we will loop over like the ranges of occurrences. So for example, let's have like something 1, 2, 1, 3, 1, 2, 1. So let's loop over 1 first. So as we loop over the ranges of 1, we would want to know if there is any range that begins from within this range, but ends at outside this range. Does that make sense? Okay, cool. We can actually use like for each element, we can actually have like a value that points to the next occurrence of that, like points to the index of the next occurrence of that value. So let's say this is the array, then I will have next, that is the array that I have just defined, the value I've just defined. So for this one, for this position, it's 3 because the next occurrence of that is this, and it's the third position. For this, it is 1, 2, 3, 4, 5, 6. This is 6. This is 4. This is infinity. It does not have a next occurrence. This is 8. No, 7. Infinity. Infinity. Okay. So we will see if like within the range, if the max of next is bigger than like the right edge of the range, then there's like a range that stems from between this, but ends outside of that. Does that make sense? Yep. So what we have to do is to basically do like a max query on next. The query, like the max query on a range on next, and you can use what range minimum query, RMQ, to do that. You don't have to use like any difficult data structure at all. And once you have defined, like once you have known that the range exists, then basically you can loop over all of the other ranges and see what is the smallest that overlap one of the range that we're looking for. And that will, yes, that will find us B.
You mentioned doing this like iterating from like smallest element first, right?
Yes.
But like wouldn't in the worst case this end up being like something n squared?
No, the number of interval is ON because each element has only one interval connected to it, right? So
yeah, but how would you check like in between the intervals in a constant time?
What do you mean in between?
Like you have to check like the first two between the first two ones, right?
Mm-hmm.
And you have to like loop inside the range is what I'm thinking.
Nope, we don't have to loop inside the range. So I mean, as long as we have found A, so this step is only to find A. As long as we have found A, we will loop over all of the B's. We will loop over like we will also loop over all of the B's, and then we loop over the ranges that contain B, and we will see if, like, for example, we will loop over 2, there's the range that contains 2, and we will see if this range, like, basically does it intersects with some range of ones, of some range of A. That's what I'm talking.
Okay, I think I see.
Yeah.
No, so for each A, what do you mean you loop over B?
No. Like if I have found like an A that is satisfactory,
Okay.
then I
Yeah.
will fix that A and then I'll loop over the B.
I see.
Yeah. So that's completely two separate parts. They don't have anything to do with each other. The only communication between the first part and the second part is that we have fixed A.
Wait, so how do we check that it's satisfactory again? Just by
So there's like a lot of ways. What I did was to basically, like, for each range, I find the next one. For the beginning of the range, I find the next one, and for the end of the range, I also find the next one. If they are the same ones, then it is not satisfactory. That is not satisfactory. So like something like this, 2, 2, blah blah blah, but it does not contain the same one. And then there's 1 here. Then the next one of this 2 is this, and the next one of this 2 is this. And if they are the same one, then it's not satisfactory. If they're not the same one, then that means that that one must be inside here and that one must be outside here. Or actually find the one before it, not after it. Yeah. Does this make sense?
So I guess what from the first region, you are basically if you have this next array, you're just trying to, if there exists something that's not infinity, then there is one, right?
Yes. Not like if there's exists something not infinity, but if there exists something not infinity and it must be larger than the endpoints of the range.
Okay, I see.
Yeah.
I see.
Then it starts from within there and ends outside.
So then if you make infinity like
Actually, it's minus
-1, then
infinity. Yeah.
-1, then you're just doing range max.
Yes.
Okay, and then you compare the range max with this region. So then you check the next one. If you didn't find one, you check the next one. If you conclude that it's starting with A works, then you iterate through the
Yes.
value of B too.
Yes. If I found an A that works, and I iterate over B.
Yeah, I suspect people use slightly different. So it's sort of, I get that some level equivalent, but will be somewhat different. So Riley, what did you use something different? Did you?
I had quite a different solution.
Yeah, I suspect what you did is probably similar to what I did.
Should I say what I should?
Sure. Yeah.
Okay. Okay, so what I did was like, okay, so wait, let me draw it again. This is L, right?
Mm-hmm.
1, 3, 2, 4, 1, 5, 2, 4. Okay, so I also compute ranges of consecutive equal values like this.
This next array.
I didn't have like a next array.
Okay.
Or well, I guess I had an next array just to compute these ranges, but I didn't like do queries on that. So then what I did was I sorted the intervals.
It's different from, I guess there are many ways that are at some level equivalent.
By like, okay, I drew it vertically, but if it was horizontally, like the right endpoint, like the second occurrence of the interval. And then, let's see. okay, so I think I visualized it like geometrically. Like suppose you have an interval and it corresponds to like some point LR. It's above like this diagonal line because L is less than or equal to R. So then what region of intervals would be good? So like let's say the interval I'm on is like it corresponds to the B, and we want to find an A interval that strictly overlaps it. So because I'm sorting the intervals and processing them in that order, it means the condition I need to meet has to do with, let's see. It means like the B, its L needs to be between L and R. So let's see. Okay, maybe I should finish the geometric part. Okay, so so it needs to have its L before BL. So it needs to be to the left of this vertical line, and it needs this R to be to the right of this. So it's like this rectangle. We don't really care about that upper line because we're sorting them. So I was kind of thinking of it like this, where we're looking for the smallest A value that has a point in here. That's kind of how I was visualizing it. And then I guess, okay, so I guess when I process the interval and I want to say if this is the A interval, I would need the B left endpoint to be somewhere inside that interval, and then B, like the right endpoint, can be anything later because it's sorted. So we only need to care about the condition on the left endpoint. So I guess it didn't end up having much to do with the geometry in the end.
You just
Maybe I
like to
should
think
do-
about geometry first.
I don't know. I like to think about interval problems that way because then, because usually it arrives at it no matter what. Okay. Okay, so basically the condition is like A left is less than or equal to, I'll just say less, is less than BL, less than AR. So like, let's say I'm processing an interval and I'm wondering if it will be the A interval for a future B. So then we have AL here, and we have AR here. That means the value A is a candidate for any VL in this range. So I do like a range update. Where I say, I want to like any value that's larger than A in this interval, I will replace it with A. So you can think of it like I'm taking a range minimum update. And then the query is a single point. The point is BL. So at a single point, I'm querying the minimum, or I'm querying what the value is. So it's range minimum update and a querying the point value. And it can be done with segment tree and lazy propagation. That was my solution.
I see. So then that's, I think my solution is really dual to yours. So let me actually, yeah, so let me share. So let me share my screen. Can I share my whole screen? I guess, yeah, I can. Yeah, so I'm just, did you see my editor window? Yeah. So Do you guys see my editor window?
Yeah, I can.
Okay. Yeah, so basically what I'm doing is I scan through and try to find the whether the thing I'm looking at now is the first occurrence of B. And then in order to do that, I want to find from this B to the next B in this range, what's the smallest number, but the smallest number. But then I only want the number here to appear if there is A already appeared before. So essentially, I use a segment tree with a point update and range query. So I'm doing range mean here, but I will add this A value here only when it already appeared. So the first time A appeared, then I will add all the later occurrence of A into this seg tree to be part of the query. So for example, I get at this point 4 will not when I'm querying at this point 4 will not show up here because this is the first appearance of 4. So I haven't added that to my segment tree. So did that make sense? So for each
So you're processing them from right to left?
From left to right, I look at each of the array and I look at this element, and then I find out where is the next it occurs. Then I do a range mean query on this on the seg tree. So my seg tree contains the elements in the array, except that some of them are not added yet. So an element is added only when it has already appeared once. So after its first appearance, I will add that the element. So the seg tree is kind of dynamically updated.
Yeah, that was the way I thought about it as well.
Yeah, I guess when Riley mentioned seg tree, I thought that was yeah, but it's sort of a duo because Riley was looking at the occurrence of A, and then as a result, somehow it's kind of the data structure is also a dual operation doing range update and then point query. So I'm doing point update and then range query. Yeah. Okay. No, let me stop sharing.
Okay, let's talk about A. Wow. Okay, A is pretty fun.
Yeah, I agree.
Non-prime factors, we know. Yeah, that's gone. Okay, A. Oh, oops. Cool. So, you have a circular array, basically. You would want to divide the circular array into exactly k segments. For example, this is 3, such that the score is as maximized as possible. So the score of a segment will be the OR of all of the elements in the segments, and the score of the game will be the end of the segment score, end of all of the segment score. And you want to maximize this value. Cool. Okay, so for like these bits, it's very common to loop over from the largest to the smallest bit and then try to turn on one of them and see if the solution still works. It's kind of like binary search, but it's more like binary lifting when you try to turn on one bit to see if the solution still works or not. So okay, so let's say, okay, so do you understand until that? Basically, we turn on each bit and then we see if the answers still work. So here now we'll have like a check function. And this check function will have like a value mask or something like that, a bit mask. And we'll want to see if we can like turn on the bits such that like we can divide the segments such that the answer must have this bit mask as like a submask. Like it must have all of these bits in the bit mask. It doesn't have to be exact, but it must have all of the it must have this as a submask, basically. Okay, so look at our condition first. It is and. So which means that if we want like the answer in total to have all of the segments, like the answer in total to have that bit mask as a submask, then the score for each of these segments must also have this bit mask as a submask because it's an AND operation. Okay, and so let's think about how to do this. Okay, so let's also have this bit mask here. For each of these elements, I will compute like how far must my if my segment starts right here, then how far do I have to travel until like I have a segment that is that is a super mask of this bit mask. So imagine like a two-pointer thing, like from here, what is the the closest I can do to have a segment that is satisfactory? Then if I start from here, this right end must increase as well, but increase like in a cycle. So we can do some two pointers to basically initialize this part. So yeah. So for each starting, we need to know how far we need to jump basically to have a segment that is a super mask of bit mask. Okay, so now after we have had like all of these ranges, how do we check? Okay, so it's the problem asks for like we need to use exactly k segments. Let's for the moment just ignore this. Let's say we want to decompose this into as many segments as possible, such that each segment must also satisfy the like the constraints that it is a super mask of bit mask. Then if we have like decomposed it into as many ranges as possible, then if the number of ranges as many as possible, let's say this number of ranges is x, then if x is larger or equals than k, we can always merge some consecutive segment together without like making each segment having this property go away. So we can always merge these segments together so that at the end there is exactly k left. However, if x is less than k, then we know that we cannot ever make k because the maximum is less than k already. Then we cannot never make k. So the problem now is basically how to compute this number. Okay, I will show you like the way I computed this number. It is an ON algorithm. It is actually very cool. Okay, so we know. Okay, so let's say that we have the ranges prepared. Something like that's too up, maybe. Something like this. Okay. And this goes to this. So actually this goes to this. We will examine, like we will only take the smallest range. We will take like the smallest range here. We know that because this is a two-pointer, this is like a two-pointer thing. There is no way that we start from something like before the smallest range and jump after to like from before the smallest range and jump right after this range because it's two-pointer. Does it make sense? Like there's no way we can jump from before this to after this range. Okay, I'll just continue then. So that means that we know that every jump must, like, if we just keep jumping, then it must somehow will have to lie within this range. So like if we start jumping from here, it will jump to here, and then it will jump to here. So it has to like, so at some point it will like at some point it will have to stay within these ranges. So if we suppose the length of this range is max, is not max, is m, then because we know that any jump can start from must have to end at some point within this range, we can start jumping from within this range, from any point within this range outside. So
what do you mean by jumping? What are you trying to do for jumping?
Sorry, I have to explain that. Sorry. So because we want to like find the smallest amount of segments that cover the same, like that cover the largest amount of segments that cover the whole array.
Yeah.
Then we can imagine like we can start from one point, and then we jump, we cover this segment, and then we jump to the next one, and then we cover the segment, and then we jump, keep jumping.
So the jump, you mean the beginning of the next segment?
Yes, the beginning of the next segment.
Okay. So yeah, I guess so if it's linear, either one line instead of circular, then it's straightforward, right? So you just do greedy from the beginning.
No, greedy doesn't work, I think.
No, for checking, I mean for checking the pattern, greedy works.
Oh,
yeah.
Yeah, so it's like greedy works if you assume you have the correct starting location.
Right. So yes. Yeah.
So like so greedy works if we know like the correct starting position, but there's like a lot of starting positions.
Yeah, so there are different ways to deal with that. So my way is to limit the number of starting position, but when you, so I'm not quite sure that then where do you start from, anyone, and then
so I claim that if I start from anywhere, then at some points like my position will have to end in the smallest range. Because you cannot jump like right over it. You have to lie somewhere within the smallest range.
Okay, so you're starting from one, you have pre-computed. Had you started from here, where do you need to end? Then you go to the next one.
Yes.
And then you keep doing this until what? Until when?
Until it loops over the whole array. Like
until it go back into your over your starting point until you.
Yes.
And at that point, what's your claim? You're claiming that number is kind of related to that number.
No, so I claim that like if I start from one, for example, if I start from somewhere, then I jump over using like the pre-computed range, then I claim that at some point I will have to jump inside of the smallest range.
Well, what do you mean this is smallest range? So what do you define this as smallest range?
The smallest range is like the range that the pre-computed range that has the smallest size.
Smallest size. So that one, okay. So you treat that as an important thing. Okay.
Yes.
And so after you find that the smallest range, what do you do?
So I made that claim. Did you understand it?
I guess I either missed it or actually just didn't understand.
Like if either like anywhere I start, if I keep jumping, I will have to at some point. So this is the smallest range that I have right here, right? Then if I keep jumping, at some point I will like step inside of the smallest range.
But why is that important? So then?
No. Like, do you get that?
No, not really. So
because if we suppose that we don't like jump into the smallest range, then that means that we jump from somewhere before the string.
Okay, fine. Yeah.
That doesn't make sense because it's two-pointer. So that means that it's like rather than start at any point, we can start at some point within the smallest range, because we know that any points will have to jump into here. So why don't we start from here?
But do you need to look at every point in this smallest range, or?
Yes, we look at every point in the smallest range.
I see. So that's
Okay.
I see.
So we look at every point in the smallest range. Suppose this range has the size of x. Smallest is x. Then we look at every point in the smallest range and we start jumping.
But is there a guarantee the complexity will correct?
Yes, because all of the range must have size at least x. That means, and we know that we have to cover like a distance of n in total. That means that at each starting point, we only have to jump n divided by x time.
Okay. Your jump. I see.
Does this make sense?
That's pretty cool.
Yeah.
Yep, and then that equates to ON.
I had a different solution for this linear part.
So yeah, you can go ahead.
Okay. So like, yeah, you can hear me, right?
Yeah.
Okay, so we have a function like x, then we'll say f of x is where it needs to jump, right? So my solution is, so remember, if we correctly say where we start from, then doing greedy for the rest works, like to jump k times and check if we jumped over where we started. So my claim is that I just jumped n times from the starting point, and then I use that as my starting point.
Endpoint.
I don't actually know the proof for this, but I did see it somewhere before. I don't know if you need n or k, but n is pretty safe.
Okay. So. Anyway, so my solution is different. So I basically, for each pattern I'm trying to cover, so
Keep going.
yeah. So I'll be essentially only the position that start adding a new bit. If I go from 0, I always try to go from 0. But then what if 0 is not the starting point, then 0 will be in the middle of someone. So then the starting point will be kind of to the left. So I look for all the points before 0 that added the first bit to it. So it gives it a bit that it didn't exist from that point to 0. So there are at most 30 or 31 of them. So basically, I just try all of them. So that's my algorithm. So basically, I try 0 and then try the 30 other points. These are the ones that are closest to 0. So they're on the left side. So they're the biggest ones that they added a new bit that no one after it added that the same bit. So then this could be a kind of a minimum starting point that's meaningful. I don't know whether that makes sense. Yeah.
I see.
So it's the complexity is a bit higher because I actually didn't pre-compute this jump. I literally just scan through greedy every time, and it turns out to be fast enough.
I think I like my solution yesterday. My linear part was correct, but like some initial solution I had, like I was lazy, so I did have like a 30 factor inside of 30 factor. So it's like n log squared of max. And it actually did not pass. So I had to like make it a little bit more optimized so it could pass. Actually.
Yeah, I guess mine is also n log squared, but it's the operation is simple enough. So I'm just basically doing bit operation every time. So it turns out to be fast.
Okay, I see. All right.
Cool.
Okay, I will start sharing. Okay. Okay, let's discuss I. So I is pretty simple. You have like you have a square. No, you have a rectangle. Sorry, you have a rectangle. N blocks by n blocks. N blocks by n blocks, or actually R by C. You will have to like select n triangles, n rectangles. You have to select n rectangles that are parallel to the axis of this rectangle, such that their overlay, like the part that every rectangle share, must have area of at least k. Overlap of at least k. And the like the what was I trying to say? The order of these the order of these things are important. So like if you have triangle A, like if you have rectangle A and then rectangle B and then rectangle B and then rectangle A, these two are different basically. Okay, so the first part is, okay, so the constraint is actually a bit small, 10 to the 6, 5,000. So 10 to the 6 is the number of rectangles. So we can think okay, so let's think about this. How about we loop over the width of the rectangle of the, like the overlap must be a rectangle, right? How about we loop over the width of the overlap, and then we loop over the height of the overlap, and then we add this to the answer. Okay, that means that we need to pre-compute like how many, like how to select n rectangles.
I still not totally understand the question. So what are there n events for n consecutive days? So what is that every?
Yes,
so basically we choose n
rectangles.
rectangle.
Yes, and
Okay,
each
so that's
rectangle is associated with one day. It is chosen.
okay. Okay,
So the order is important.
So the and k. So we want to be able to choose n rectangles
such that their overlap, like the area that all of the rectangles share,
is
must
at least
have
k.
yeah, must have area of at least k.
Okay. Okay.
Yes, and yeah, so okay, so my claim is that maybe we should do something like 4 over the width of the overlap part and 4 over the height of the overlap part. And if this is larger or equal than k, then we add something to the answer, like the number of ways to choose n rectangles such that their overlap on width is exactly w and the overlap on height is exactly h.
So the overlap of all of this rectangle has also to be a rectangle, right?
Yes, they have to be a rectangle. So yeah, so we have 4 over a w of 4 over h. So one very important thing to notice is that the width and the column are completely independent from each other. So because you can imagine, like, to build a rectangle on this grid, you can imagine choosing 2 columns and then choosing 2 rows and then selecting like what's between those 2. So we can see that like the width part and the height part is completely independent from each other. So we can try to pre-compute like how many ways to choose. Sorry. So because we need to do this, we can basically pre-compute like how many ways to select the ranges on an array of size C such that their overlap is exactly W. Does this make sense?
Mm-hmm, yeah.
Okay. I think, yeah, with on size C, yeah. So I did this DP I use a DP and inclusion exclusion. I did a DP where DPLR is the number of ways to choose n ranges. Remember, we have like an array of size C, array of size C. We need to choose ranges such that their overlap is at least W. So DPLR is to choose n ranges such that their overlap is a range that covers L, is covering L, LR. It does not have to be exactly LR, but it's covering LR. So how to do this? So DPLR is actually not a DP at all. We can calculate it using some math. Because like the overlap must be covering this range LR. We know that for each range, its left positions must be to the left of this L, and its right position must be to the right of this R. So we can use some formula to calculate that out. It's actually L plus 1 times C minus R plus 1. This is how many ways we can choose the left column that is to the left of RL, how many ways to choose the right column. And then we have this power to n because we have to choose n ranges. Okay, does this make sense? Okay. However, this is like only covering like LR. What we're trying to do is to eliminate this covering part because it's really annoying to deal with. We want to know like how many ways to choose n ranges such that the overlap is exactly LR. So how to do this? So we can use inclusion exclusion. Let's have a new tab actually. So we can use DPLR, but this is like the range is only covering LR. So it can maybe cover LR plus 1, 2, or maybe it can cover L minus 1 R. So we need to subtract this. R plus 1 and subtract it from L minus 1 R. But we see that these two have one overlap. That is, the range is covered, the overlap is covering the range L minus 1, R plus 1. So we need to add that back to compensate. So that is DPL, L minus 1, R plus 1. So this formula is how many ways to choose n ranges such that their overlap is exactly LR. Does this make sense?
Do you need to do this inclusion exclusion all the way, or just this for?
Yes, we need to like. What do you mean all the way?
I mean, it's like you need the -1 to the power of for distance 1 for the length 1, then.
No,
then you also
think,
consider L minus 2 R or something.
I see. I don't think that it's needed because due to like the definition of this DP, it's like choose n ranges, overlap is covering. It's not exactly. I think if we define it to be exactly, then we have to like do the inclusion exclusion part all of the way. But because this DP is like only covering, it has compensated that fact for us. So we don't have to do it all of the way to the left border or to the right border. So this part is.
It's quite similar to doing like a prefix sum, like the equivalent of a prefix sum on a rectangle.
I can see where that comes. So if we extend this, so yeah, we add this part, and we subtract. Oh, oops, we subtract the thing. We add back like the overlap. So yeah, so this is what we have. So this is what the number of ranges that covers exactly from L to R. So we can also have like another array that is PR. That this is what I defined in my code. So PR of I is the number of ways to choose n ranges that its overlap covers a range of length exactly I. So since if we have calculated this answer, we just add this answer to R minus R plus 1 or without plus 1. It depends on how you define it. We add this value to this PRI. Does that make sense?
Not totally, but that's okay.
I think it doesn't make sense to me too. Okay, so the thing is,
I think at this point I feel just if I learned a few things from here, then that's good. So I guess one thing is you consider rows and the column totally independently, so which happens quite a lot with
yes.
this kind of a grid problem, and the other is to use DP this way. Yeah. So yeah, I'm perfectly happy. Yeah.
I really think that in some sense you don't have to completely understand your solution. Like I had a lot of trial and error before I came up with this solution.
Okay.
So yeah, so okay, so this we can submit this, but however it will give TLE. Okay, so let's go back. Why does this TLE? It is due to the fact of this. If we do this naively, then when we calculate dPLR, we have to use like the power function. So that gives us the complexity of O R squared times log of n. Yes. This is bad. It does not fit in the time limit. So what we can do is to distribute this n into the two. And we realize that this L plus 1 thing and C minus R plus 1 thing is within R. So we can pre-calculate like the power of U to N with all of the U from 0 to R. And this will give us the complexity of O R log N plus R squared. And this will AC. This will not AC. This is what I learned in the hard way. This is I mean, this is bad. This is just bad, I think. Like trying to do something that is not completely necessary. But yeah, you need to pre-calculate this part. So yeah, so to sum up, there are free pre-calculations. Oops, should not have sold this. So to sum up, there's 3 parts of pre-calculations you have to do. That is problem I. First, you need to pre-calculate the power, and then you pre-calculate the DP. DP, you need to do it 2 times, one for the row and one for the column. And once you have the DP like this, you can then use this formula to add it to like use this, like the number of overlaps that has of length of exactly I. You need to add that. So yeah, that's free pre-calculation. Yep.
Okay.
Okay, cool. Very mathy problem. Okay, the last problem is okay. Okay, so for this problem, you will have also a rectangular grid, and there is like a pebble that is placed initially on. There's one pebble that is placed initially. So what you can play a game with these with this rectangular grid. So at one point you can basically insert a pebble either from the bottom, from the top to the left or to the right, and you can basically just push it until it hits a pebble that has appeared there before. And when you push it and it hits like a pebble that has appeared there before, it stays at that position, like one below that pebble, or one left or one top or one right. So you can continue playing this. Okay, cool. So for a configuration that is a tree, that means that each pebble is only connected to every other pebble via one path, where like 2 pebbles are consecutive if they are 2 pebbles are connected to each other if they are consecutive. So with a configuration that is a tree, you want to know if like you can make that configuration happen. So for example, for this configuration, this is the tree. This is the initial pebble, and this is the configuration we want to reach. You cannot make this configuration because whatever you do, you have to go along this path, right? And when you go along this path, you will have to insert this pebble. And this pebble can be only be inserted if it is brought from the right, from the left, and it hits this pebble. However, if it's brought from the left, then it will hit this pebble first. So there's no way we can insert this pebble here. So basically, you're given like the initial pebble and the final configuration of the pebbles. That is a tree. They're guaranteed to be a tree. Yeah. You want to know if it's possible to make that configuration, and also you want to output like how to make that. Okay. Oops. So the first thing we know is that because it is a tree, we can actually know because it is a tree and it has like the initial pebble, which we will consider it to be the root of the tree. We will know like exactly for each pebble which direction it will be, like in which way it will be pushed in. So for example, because this is the root, this pebble must be pushed in from the top down. This pebble must be pushed in from the top down too, because it will hit this. So you can use some DFS to basically pre-calculate that for each pebble, how it will be made. But yeah, that alone is not good enough. You want to rearrange like the moves so that no moves will overlap, like no moves conflicts each other. So for example, I'll give you a very small example. Okay, so for example, if you, okay, so if you start from this configuration and you want to make this configuration, then you will want to push this pebble, the second one in the top row first before pushing this pebble, because this pebble can only be pushed in from the right. So if you make this pebble come here first, then this pebble cannot come there. But however, if you have pushed this pebble in, then you can continue with the rest of the path. Okay. So how do we do this? Let's consider for a row, for example. Let's consider for a row. We will see that for each pebble, if this pebble is pushed in from the right, then that means that every pebbles to the right of this pebble must be pushed in after this pebble has been pushed in. So there is an order. You can think of it as an order. So this pebble must be here before these. So this will lead us to think about some sort of topo sorting. That is, this must be ordered before this. And along with like the original DFS topological order, you can basically build like a grand order of these pebbles, and then you can topo sort them. So the question is how to, okay, so we have like the initial DFS topological order already. So the question is, how do we generate these? That is within limit. So let's say we go from the right. So there's like a very big case, something like this, but just magnified. Wait a minute. There we go. So something like this. So we can see that this pebble is pushed in from the right, so it must be before these two. This pebble must be pushed in from the right, so it must be before these four. This pebble is pushed in from the right, so it must be before these six. So you can see that it is quite a bit of work actually. There might be on squared such orders, because we can just generate this path, just go along to the left, and we can make each pebble relies on more and more pebbles going after it. Okay, so what is our optimization here? The optimization is actually pretty nice, I think. So let's think of it like this. We know that this pebble must rely on these two pebbles, right? And we know that this pebble must rely on these four pebbles. But however, we know that this pebble has already relied on these two pebbles to go after it. So we can actually remove these two pebbles from the configuration and say that this pebble only relies on these two. Does that make sense? It's basically something like along this line.
So yeah, I guess the high level idea makes sense, but it's but
So-
how do you actually?
So the high level, so it makes something like this. So this, let's say this is the first top node. We know that this pebble must be before these four. However, let's say that this pebble represents this one. This one represents the left one. This one represents the right one. And this one represents the left one. We know that this pebble must rely on these four. However, this pebble has already relied on these two. So that means that these edges are not necessary anymore. We can just simplify it to be something like this. Simplify it to be something like this. Does that make sense?
Do you need some kind of union find or?
No, you don't have to use any union find. So basically what I did was like, if we have already had a pebble that relies on every pebble to the right of it, then we can just remove every pebble to the right of it because they are not needed anymore. And then you keep going.
So how do you check the one is depend on the, you can't go through all the pairs, right? So
you cannot go through all the pairs. You can go through some form of like the original one that I told you. Okay, so let's see how I can explain this. So a pair may be like depending on each other if they're on the same row or column.
I think a good way to explain it is like you have a stack, and like as you scan it in one direction, you like if a pebble doesn't rely on anything that you visited before in that direction, then you add it to the stack. Or you add it to the stack no matter what, and then you remove, if it relies on things before it, then you remove all of them because it's sort of representative of everything it saw before.
But I guess just still this optimization aside, just how to find the dependency. I'm not.
So okay, I'll start talking. So how to find the dependency is you loop through each row, and then you will find a dependency over the row, like to the left, and the dependency over the row to the right. Okay. And same for each column.
Okay.
And we know that because in total, like the number of pebbles is like ON. Yeah. So we can just loop through each of the row and then loop through each pebble over the row without like a big cost because in total it's just ON.
Okay.
So after we have all of the dependencies, when we can basically topological sort them.
Okay, cool.
Yeah. Okay, so I want to talk about something first. I bugged on this problem for 40 minutes yesterday. And then after like 40 minutes of debugging, I only realized that I haven't sorted the pebbles on the row by order of I or something like that. So yeah, so that's a precautionary. If you want to do something, then you have to sort it first. If you want to do something in order, then you have to sort it first. Yeah.
Okay.
So
okay, cool.
So that's K. That's K. H. We can talk about H, but I think
no,
it's
I think
like
that's
too bad
enough.
of a problem.
Yeah, I think that's
too bad
enough.
of a problem to be discussed about. Yeah.
Okay, good. Yeah, thank you.
Okay, thank you.
Yeah, thank you.
So see you next time then.
Yeah, let me do that. Did I still
I think I can leave. I can just
stop?
leave.
Yeah.